Hello, hello. Welcome to our next talk at PyData Global on the third and final day of the conference. We are really happy to have everyone joining us, so thank you. I'm very excited for our next talk by Avik Basu. He is going to be speaking on Beyond Just Prediction, Casual Thinking and Machine Learning. And Avik is a seasoned machine learning engineer and data scientist who is passionate about developing tech that enhances people's lives. With deep expertise in scientific Python and a proven track record of building impactful ML solutions, Avik focuses on creating systems that address real-world challenges and improves people's lives. So with that, I'm happy to hand it over to Avik.
Yeah, thank you so much. So, hey everyone. Good morning or good afternoon. I hope you're doing well. Today I'm going to talk about causal thinking in machine learning. Now, this is something that new to me as well, but I've gained quite a bit of interest in this. So let's look into this together on this. So a little bit about me. So I am based in Sunnyvale in the Bay Area. I'm a data scientist, add into it. I'm also an editor at PyOpenSci, which is a nonprofit for broadening the acceptance of scientific Python packages. I come from both an engineering and a data science background, so I like to be in that sweet spot where I can do both things. I love gaming. I love PS5 and recently Steam Deck. If any of you are a gamer, please look into Steam Deck. I love soccer and tennis. And I also like driving because I really feel that driving is therapeutic if some conditions are met. And this is me driving, at the Laguna Seca. So it's a track nearby, and it was a blast. All right, with that, let's get started with our agenda. So the goal of this talk is to give you all an intuition behind causal thinking and how can we use it for our own use cases. So we'll go over the classic correlation versus causation topic. Then we'll go over some concepts related to causal inference. And then we'll move on to uplift modeling and how to evaluate those models and just end with some practical takeaways on those. Okay. So let me start with a scenario many of you probably have encountered. Okay. So we have a prediction problem, which is basically a customer churn. So the problem is that we build a model to predict customer churn, right? And the F1 score is 0.9, so it's really, really good. Okay. So you're feeling pretty good about it, right? And the model basically learned that probability of churn given that they call support is 45% versus only 15% if they didn't call. Okay, so your model is very confident about this pattern, and it's basically saying that customers who call support are 3x more likely to churn. So someone from the business team just says that great, okay, that's really awesome. Okay, how do we just reduce, how do we just reduce support calls to prevent churn? Okay, and this is where we really need to pause. The thing is that you know did support calls cause churn, or did unhappy customers call support? That's the big question mark here. Okay, so your model can be 90% accurate but still lead to a completely wrong business decision if you confuse prediction with causation. Okay, so that's kind of the theme here, right? So the key insight would be like high accuracy does not equate to an actionable insight. So let's look at the classic correlation versus causation thing, right? And let's formalize the distinction between the two. So in the case of the predictive models, like a traditional machine learning model, we estimate e of y, or expectation of y given x. Okay, and we ask the question, like in this case, for example, that who will buy, and the answer that we are looking for is what is going to happen, right? But in case of the causal model, you are actually looking at it something different, and we are actually estimating expectation of y1 minus y of 0 given x. I'll actually explain all of those terminologies in detail later on, so don't worry about that. And then the question we are asking is who will buy because of the treatment. Okay, and the answer we're looking for is what is the effect of our action, not what is going to happen, but what's the really effect. Okay, so these are actually fundamental different questions with different approaches which are required for this. Okay. All right, so let's take a concrete example which we're going to use throughout the talk. All right, um, and the example is this. So the problem that we have is that you run an email marketing campaign and you want to measure its effectiveness. Okay, so, and in this case, let's say we have a prediction model, and it just says that 20% of customers who got emails purchased, right? So, pretty plain and simple. But in the case of a causal model or an intervention, uh, we are basically seeing that expectation of purchase given t equals 1 minus expectation of purchase given t equals 0 is 0.05. Now, t equals 1, t meaning treatment equals 1 means that email is sent, and 0 means that email is not sent to that customer. Okay, so here what we are seeing is that sending email increases the purchase rate by 5%. Okay, so we're looking at the same data, but we're asking the different questions here. Okay, so we are measuring the actual effect of that intervention here. So uh, now let's just imagine in the same example of the email, right? This is your campaign results. Okay, if you received an email, you have a purchase rate of 20%. Okay, and no email, which is the control, or the control group, is 8%. So a simple math that email boosts purchases by 12 percentage points. And we just say, okay, ship it, right? Well, not so fast. This might be the bottom line, but we are missing something here. Okay, so the question we need to ask ourselves is that who got these emails. Okay, and your marketing team was not sending them randomly. They actually targeted recently active customers and people with high engagement history. So that is the main problem. So the email recipients were recently active, they had high engagement history, and the people who did not get any email were actually inactive customers, and they had very low engagement history, basically. Okay, and here's the problem, right? Engaged customers are more likely to purchase regardless of the email. So that 12% difference that we saw, it's not all from the email. I mean, some of it, it's just that engaged customers will buy more anyway. So the observed difference is actually the true effect plus the selection bias. So now let's talk about the selection bias, right? So in the real picture, so when we actually break it down by the customer type, here's what we see. So in case of the high engagement, so just let's look at the top row, right? The high engagement. The so in the treatment group, we have 20% purchase. In the control group, which is they did not receive an email, we have 16%. So the true effect of the high engagement cohort is actually just 4%. And similarly, in the next one, if you have low engagement, well, if you send them an email, it's only 6%. And then the no email group is like 3%. So the true effect for the low engagement is actually 3%. Okay. So now here, one thing to note is the customer engagement feature, this high engagement and low engagement, is actually what is called a confounder, because it affects both who gets the email, which is the treatment, and who purchases, which is the target variable. All right. Now, how do we solve this problem? Well, the only way to solve this problem is actually, or I would say the gold standard for this is randomized control trials, which is basically A/B tests. Okay, randomized A/B tests. So the key idea being that random assignments ensures treatment and control groups are identical at the baseline. So, for example, in this case, if the marketing team had done their job, well, after randomization, the treatment group with email is basically random 50% of all customers. Okay, so that would be the treatment group, and the control group will be random 50% of all customers again. Now, if the groups are identical on average, then what we see as an observed difference is actually the true effect. So any difference we observe is actually the true effect of the email. So randomization breaks the link between customer characteristics and the assignment treatment. Okay. So, but what is the problem? Well, the problem is that A/B tests are expensive. Okay, they take time to run. Sometimes they're unethical. I mean, you can't just randomize medical treatments, right? And often we have already collected the data. So the campaign already has happened with biased targeting. So what do we do about that? Well, we have to ask this question, that how do we estimate treatment effects from observational data, right? And this is where uplift modeling comes in. All right. So in uplift modeling, basically we have three key components that we will go through one by one, but here's what we need to think about them, right? First is the potential outcomes, how to think about treatment effects. Okay. The next one is conditional average treatment effect, or the CATE, right? And this is exactly what we are trying to estimate. And the third one is, how do we do that? Like, how do we estimate CATE? Okay, this is actually the technique for estimating CATE, like one of the techniques, I would say. So let's go with the potential outcomes framework, first of all. And how do we think about the treatment effects? Well, we need a framework to think about them. Okay, the idea is simple but pretty powerful. So for each individual, there are actually two potential outcomes: y of 1 of 0, which is the outcome of person I if not treated. 0 means it's a control group, which is if not treated. And y of I of 1 is outcome, like for a person I if treated, meaning that they are in the treatment group. All right. So so the individual treatment effect is basically y of 1 minus y of 0 for a person I. And that exactly was what we saw in the first few slides about the expectation mechanism. All right. So now here is the problem. Okay. Um, so let me just go over so that it's pretty clear. So let's take an example that Maria got an email, okay, which is t equals 1, and did a purchase, which is y equals 1. Uh, Again, t is the treatment variable, y is our target variable, okay. We observe y of 1 equals 1, right? I mean, she did get an email, and also she did, so I mean, she actually did a purchase. But we do not observe y of 0, right? Why not? Well, we can't just rewind time and try another scenario. I mean, Maria has already got an email and has done the purchase, right? So we do not observe the y of 0, which is called the counterfactual. So counterfactual, you can think of it as a what if question. Okay, so we can never observe both outcomes for the same person. Okay, so would she have purchased without the email? Well, if that's the case, then y of 0 equals 1. In that case, our individual treatment effect would be 0, because that person would have bought it anyway, right? But if y of 0 equals 0, which means the ITE equals 1, and in this case, well, the email caused the purchase. So it actually the intervention which really made the purchase happen in that case. So that's kind of the whole framework and the problem that we have with the counterfactuals. Um, the next one is, I mean, but if you think about it, why does all of this matter anyway? Okay, and the thing is that just like these two people that you can see respond differently to olives. I mean, one loves it, one hates it. Individuals respond differently to interventions. Okay, so if we just look at the average treatment effect, we might see it as 0 and conclude that the intervention does not work. But it actually works. It's just that it works on different people differently. Okay, so individuals respond differently to interventions, and that kind of gets hidden in the average if you just look at it. So which actually brings us to four types of people. In fact, there are actually four distinct types of customers. So let's imagine this hypothetical scenario where we can see both potential outcomes. So there are no counterfactuals. Let's just imagine that. Okay, so we have our first customer, Mr. Grayson, and 1 meaning that that person purchased, 0 meaning that he or she did not purchase. Okay, now Mr. Grayson received an email. Okay, when if received an email, he did purchase. If he did not receive an email, then also he did purchase. So ITE is actually 0, and this type of customer, we call them as sure things. Okay, meaning that they would buy regardless of what we give as intervention, right? The next one is Mr. Drake. Well, in this case, they received an email. When they received an email, they did purchase. But if Mr. Drake did not receive an email, like he did not purchase. So the ITE is actually one. This type of customer, we call them as persuadables, meaning that if we intervene, we can actually persuade them to buy. The next one is Miss Gordon. She did not purchase when she received an email. She did not purchase when she didn't receive an email, and the IT is zero basically. And basically, she did not purchase regardless. So this person is kind of known as the lost causes. And then finally, we have Miss Kyle, who did not purchase when received an email, but did purchase when the email was not received. So it's kind of weird. So the IT is negative. So this person is basically sleeping dog. So they would actually purchase if they didn't receive anything, but if they did receive something, they will not purchase. So we do not want to target these people. Okay. So now notice that the average treatment effect, if you just sum this ITE column here, is actually zero. But the truth could be, so I mean, like, it couldn't be further away from the truth, because um, I mean, we see that there are different kinds of people who are behaving differently to the intervention. Okay. So, but really, persuadables are the people that we care about. They have a positive treatment effect and they convert because of the intervention, right? So these are the kind of people we want to target. Okay. Now, but that was some hypothetical scenario, but the real world problem is different, right? Because our ITE is actually unavailable, and that's because we never observe both potential outcomes. So every person is either treated or not treated. We can't see them both. So we can't directly compute ITE for everyone. And that's where, calculating the conditional average treatment effect, it comes into play. And this is what the uplift models predict. And the problem here is, as we said, that we cannot observe ITE for any given individual, right? Um, but the solution is that conditional average treatment effect is the expectation of y of 1 minus y of 0 given some features. So in plain English, Kate is actually the average treatment effect for people who look like X. Okay. By grouping similar customers, we can estimate their expected uplift, even though we can't see their individual counterfactual. So that's kind of the whole concept here. So in that same table, we could have our predictions from our uplift model, in these blue cells, and now we can calculate the conditional average treatment effects. So these estimates are actually Kate estimates from our uplift model. All right. Now let's now think about how we can compute all of this, right? So now we come to the concept of meta learners. Now there are actually other methods as well, but I'm going to be focusing on the meta learners for this talk here, because these are most widely used usually. Okay. And these are basically a way to leverage predictive ML models for estimating treatment effects. So we're going to use a traditional machine learning model to predict or to estimate these treatment effects in the causal setting. So that's really what we're trying to gain here, right? And the best part about this, which I think is the best part, is that the underlying predictive model can be of any model type. Okay, meaning that it could be a neural network, it could be a decision tree, it could be a gradient boosted tree, it could be an SVM, you name it. It could be really anything. Um, and the problem also could be anything. So the predictive model can be estimated regression or classification. So in case, let's say, like in this case, whether they would buy or not buy, it's a classification problem. But you can imagine that there's a problem about revenue, or increasing revenue for a company. In that case, that would be a regression problem. So really, the choice depends on the problem itself. And of course, there are different types of meta learners. There's an S learner, there's a T learner, and there's an X learner. Okay, but for this talk, I'm going to focus on S and T learners here. Okay, so let's look at S learner, what that does. So imagine that this is our training data from our randomized A/B tests. Okay, so we have our features, which is X1 and X2, which is engagement and the tenure. And it's the same problem, by the way. So it's the email sending and buying problem. Is email sent is our treatment variable, and is purchased is our target variable. Okay, so the idea is that we train one model on all data, with treatment as a feature. So you imagine that T is actually a feature with X. Okay, that's kind of the whole thing, right? So it predicts both outcomes and it computes the uplift. All right. The best part about this is the simplest technique, and it works great as a baseline, in my opinion, and it works well with limited data as well, right? You can imagine that you're not training, two or three models; you're just training one model, and it just works well with limited data as well. The caveat to that is that treatment is just another feature. So if you're thinking of capturing some complex interactions, it might not be able to do that because it is just one feature for them. Um, and in and in terms of pseudocode, it is something like this. So when you have your feature, you have your features, you have your treatment, you combine them into one matrix basically. So you combine them into features plus treatment. So you add the treatment as a column, and then you train your model. So in this case, I'm training a light GBM model, and then I fit with the X combined and a target variable Y. Now, uh, what we really need to do is that we need to calculate y1. Now, y1 is what? Is basically, yeah, the prediction given x, which is the features, but t equals 1. So you predict of all features x, but t equals 1. And then y of 0, the same thing with t equals 0. And then you compute the uplift, which is denoted in the literature as tau, right? So you have y1 minus y0. And that is actually your conditional average treatment effect. Okay. Now, in case of the T-learner, it is different because in this case, what you're really doing is that you actually separate the two models. So T-learner basically means two model approach, but I would say at least two, because if you have more than one treatment, it can get more than two models. But it's really that it has at least two model in this case, right? So again, so you separate the data into whether they received a treatment or not. Okay, so the model 1 would be trained on email recipients, and model 0 would be trained on no email, so t equals 0. So you train these two things differently. And the good part about this is that now it can understand different patterns in treatment versus control, because you have two separate models for each. Okay, and it's able to capture better heterogeneous treatment effects as a result. And I think the best part about them is that you can actually tune these two models differently, meaning that maybe you need a more complex model for model 1 when it needs to understand the treatment, but then for model 0 you don't need that complex of a model. But again, the caveat here is that you need sufficient data in both training groups, in both groups, right? Because the more models, you can imagine that you would need both training data there. And if I think about the logic or the pseudocode behind that, it's basically this. So you have this function called split by recipe. Let's just imagine, which splits the data by each recipe. So you have X treated, X control, Y treated, and Y control. And then you train the two models. So if you first train the treatment model, which is the model 1, and you fit with the treated data and the Y treated. Okay. Then you train the control model. Here you can notice that I used a different model for control. It's just a random forest classifier. And in this case, you fit with X control and Y control. Okay. And the last step is still the same, right? Because you're basically computing the conditional average treatment effect, which is the uplift. And in that case, it's y1 minus y0. Now, what is y1? Y1 is model 1 dot predict of X test. And model 1 already is basically considering only the treated people, right? So you don't need to do any kind of magic there. So y1 is basically model 1 dot predict, and y0 is model 0 dot predict of the same data. And then tau is y1 minus y0. So it's pretty simple there, but this works really well. But I think a good rule of thumb is always to start with an S-learner to see how the baseline is. Now let's talk about evaluation. And this is kind of tricky because it differs from the traditional evaluation metric. And traditional metrics like accuracy and F1 measure how well we predict outcomes. But for uplift models, we need to predict treatment effects, and that's fundamentally a different thing. So basically, in case of the accuracy in F1 score, you predict how well we predict Y. But what we really need is that how well we can predict the uplift, which is Y1 minus Y0. Again, what it really measures is who will buy, but what we need is who will buy because of the treatment. So a model can predict perfectly who will buy, but they might completely fail at identifying who will buy because of the treatment. So we need some different metrics. Now there are different metrics or different techniques for uplift evaluation, but here I'm going to focus on one of them, which I found pretty useful from a practical perspective. Okay, so
And just Avik, sorry to interrupt. We're at the 5-minute mark.
yeah,
So
cool.
Just wanted to let you know that. And if anyone has any questions, please feel free to drop them in the questions chat.
Yeah, cool. Yeah, I'm not that far away. So, all right.
Awesome.
So,
Thanks.
yeah, so the first thing that we do is we rank the users by predicted uplift score, which is basically, in descending order. So we rank the people who are more, or which the model thinks would be most affected by, positively affected by the intervention. We, treat them first, or we line them up first. Okay. Then we divide them into bins. Like, for example, let's say we divide them into 10 bins. All right. Now, after we divide them into 10 bins, we actually calculate y of 1 minus y of 0 of b, right? Which is basically the bucket b. And that's what we're doing here. So y of 1 of b is the average outcome in the treatment group and bucket b, and y of 0 of b is the average outcome in the control group and bucket b. And that's what we calculate. So we calculate the uplift for each bucket there, okay? And it looks complicated, but it is really not. It's just the way to really calculate the uplift in each bin there, right? What we really have is that in case the model has been trained well and it's a good model, the graph will look something like this. So we'll have a monotonically decreasing curve, and then you could see that the first bins, like bin 1 for example, has shows the highest uplift, which is what we expect because we group them like that, right? And as we go along the lines, we see less and less, and after actually bin 5 to 8, we see a negative uplift, which meaning that if we actually treat those people, we will lose money because they will not convert. So these are those sleeping dogs, like for example. Okay. um, so the best takeaways here is that in the best case, we expect a monotonically decreasing pattern as we move from left to right. If the uplift rises or stays flat as the bins increase, it suggests that the model is probably overfitting. You might need to take a look at that. So this is kind of a sanity check for the model. Okay. And if the early bars are close to 0, then the model has a very weak uplift, and you need to probably either make the model less complicated, or you might need to gather more data. Okay. And if less data, then it's better to use fewer bins to remove the noise, because otherwise, if let's say in one bin you have so little data, it would probably be noise. So you need to be careful there. Okay. Now there are multiple targeting options. Now you have this graph, right? But how do you deploy it in production? Meaning, like, how do you target people in production? But there are multiple strategies for that. Like the one very simple strategy is target all positive uplift, right? So more customers are reached, but in this case is bins 1 to 4. Okay. You can reach more customers, but you really get lower average uplift per customer because you're being a little bit conservative there. Okay. The next one is target only the top uplift, which is bins 1 and 2, which basically is a fewer customers but highest impact, and it's a better resource efficiency. Okay. So these are, two different techniques you can just choose there. I'll just go quickly on this. We have this criteria data set. This is a working example you can see in the GitHub link that I'll share next. But this actually shows how the t-learner and s-learner perform for a given data set. So the key takeaways here: when to use uplift modeling? Well, I would say when you can't treat everyone and you can't have A/B tests, or you do not have lots and lots of money, then I think uplift is a pretty good thing to target, because treatment has cost. It has time, money, ethical reasons, and customer experience, and we need to optimize who to target. So if that's the thing, then I think it's better to use uplift. So you have limited budget and limited capacity. Now you can also stick with traditional
I
ML.
apologize. We're at the very end. I've got to end the session so the next one can start
Okay, cool.
at the 10:30 mark. Thank you so much. If anyone wants to ask any questions, the Discord link is in the up in the website here for you. Everyone have a great day, and thanks again, Avik.